All right, okay. Thank you so much, everybody, for sticking around. Yeah, it's evening already over there in Europe. It's morning here where I live. So my brew is still coffee, although they say, well, beer is not just for breakfast anymore. But anyway, so let's dive right in. Maybe first, a thank you to David and Michael for setting everything up for these classes. And of course, always to Richard and all the technical team for relentlessly improving the Yocto project and the build system and everything, and keeping everything updated and rolling along with all new releases for Linux kernel and whatnot else. So who I am, I'm Rudy Streif. I run a small company. It's a consulting and development company. We do a lot of software developments for our customers with the Yocto project. We also do hardware development. We developed a computer, embedded computer for one of our customers that will go into an espresso maker, essentially, and an oven that's going to come out early next year. So the fun about being, of course, a consultant is we work on a lot of different projects. For me, it goes from military security devices over vehicle infotainment all the way to household appliances and things. All right, good. What are we going to talk about today? And please, yeah, so I'm ask questions. I'm looking as good as I can also at the chat window and the IRC chat there. And if you have a question or so, please ask a question through the chat. I'll be happy to answer it. So what are we going to do? So so once you have your Yocto project system running, you have your operating system, maybe your base images running or so. Okay, good. But you want to develop a device or something that actually does something for an end user, and which normally means you'll have to add additional software packages to it. Now, David has been talking about the dev tool, which is a great tool actually to do that job. To add your own things to your Yocto project builds. But we'll also be looking about some typical tasks you have to do after that, beyond creating the recipe and compiling. And one important thing is actually packaging. So how do you actually put these artifacts into packages that will be installed on your target root file system after it has been built? And then we also talk about package installation scripts. If you have to modify your installation or do some additional configuration steps after it has been installed into your target's root file system. Talk about package groups, how to group things together, multiple software packages that then can be installed by the build system as one. And often, in particular, if you have embedded devices representing some sort of a user interface or do some other things, you will have system services, so you will want to launch these at startup. And there's a lot of these things that goes into all of these tasks. And we're just going to be scratching a little bit on the surface of that and how to accomplish that. All right. So here's the lab setup, and we'll go through this. So you should have your virtual machine here from DigitalOcean, and you have your YP Summit November 22 and a link to a Scratch directory. So you want to change directory into YP Pokey, and that's the same as it was with David's class before. There should already for you be set up a work directory here for build user space. So you just want to source that. And if you followed the previous class, maybe it's a good time to actually change or to close out your terminal, log in again, so you start with a new environment. So we typically do this, and I use the source command explicitly. Of course, you can just use the dot, but in a present environment, writing it out is probably a little better. Okay, so we're in this build environment. And if you follow along with the slides, so you should see the class configuration at the end of conf local.conf. So you just can check that. So this should be just there. So we set the machine, it's already preset. I think it should be the case for your setup for your virtual machines too. We use an emulated machine, QEMU ARM64 architecture, solid shared state cache directory, as well as the download directory. Everything be set up already. Some features be set up. That's all good. And we have some extra image feature, which is good for this class. So if that's all okay and looks good for you guys, you can just move on to the next setting, the next slide. Just to check if everything is built correctly, we just want to run quickly bitbake -k core image base. That should actually just return. Just start bitbake quickly up and then discover that everything has been built already and set there. And finish right away. All right, good. So if you're following along, this should quickly be looking the same for you. So if it doesn't, let me know. If it's okay, give me a thumbs up. If I'm moving too quickly, also let me know. Good. All right, also quick test. Run QEMU, no graphic, QEMU ARM 64, just see if QEMU is working. No graphic means, of course, we don't need a graphical user interface. For that, you would have to set X window forwarding setup. And QEMU ARM 64, that would be the machine. So just see if it's actually working. All right, here we go. Kernel booting. All right, this host key thing sometimes takes a while. Need some random generator input. Oh, we're asking for sudo here. So your sudo password is actually the registration confirmation that you got from the Linux Foundation. The registration confirmation number. The entire, yes. Okay, we're good here. You can of course log into it. If that works is good, then you just can shut it down again. And we're good. All right, good. So we're back on our virtual machines command line. Well, multiple virtual machines. QEMU is also a virtual machine, but in this case, a DigitalOcean virtual machine. Everything good? All right. So next step is we're creating a layer with DevTool actually and a workspace. And DevTool create workspace meta user space. Bring this back. Here we go. All right. And if you now use the ls command to show, so this meta user space layer has been created. Typical layer configuration, there's not much in it right now. It's just the conf subdirectory and the layer configuration file. And this also should be added automatically already to your BB layers. So that is from your build environment, bblayers.conf. And here you see your build user space, meta user space has been added to your layers. If that's all good for you, we're ready to go. It's always a little bit harder to do these virtual classes because we can't see your faces. If your faces say, yeah, thumbs up, or I'm having a problem or so, then it's hard for me to see. Okay, So we're using a couple of examples in this class, and they also, wait, okay. Def to create meta use space equivalent to bit bake layers, create layers. Yeah, yes, in that sense, yes, it is. That is correct. It just creates an empty layer and it adds it in one command. So you could use a bit bake layers, create layer, and then meta user space, and then add your layer to it. Good. Any other questions? Great questions, by the way. Yeah, it's not obvious. All right. So we have a couple of class examples. It's actually source code that I prepared already. And on the DigitalOcean machine, and I'm just switching to another terminal here. So that should be actually in Scratch source, and then there's user space. And you should have these two lab packaging and lab system service. And we will be using this path, excuse me, throughout the slides. So if you put this into a different path, or if you use a local machine, then we would have to adapt the path in the commands that you'll see later in the slides. So question, everybody set up with the sources? You have these sources available to you? Or I take that as a yes for now. Oh, didn't expect tarball yet. Okay, yeah, do that. If you need more time, let me know. We have 1.5 hours. All right, we lost some time in the beginning, so we have 1 hour left before the social event. Yes. Yeah, if you need to extract the tarball, you can create your Scratch. You can. So I don't know if you're working on a local machine or if you're working on the DigitalOcean machine. But if you have the tarball, and if you're in the Scratch directory, and then you go into SRC, and then you can just simply extract YPS 2022.11-user space tar.bc2 into this. All good? All right, let's go. Move forward. Packaging. So building software packages, I think you're pretty much familiar with it, what you normally do. And this is what the build system does, essentially. First, of course, you fetch the sources from upstream or from any repository or whatever you have locally. We're talking about your software packages. In that sense, that can be on a file system, of course, can be in Git repositories on your own GitLab servers, or of course also upstream some sort of Git server, or downloading via HTTPS or whatever it is. That's for what BitBake has all these various fetchers available to do so, which you specify, of course, in src_URI in your recipes. Then you have your repository, or you have your archive, and then you often have to extract maybe a tarball or so to, of course, get to your sources. Yeah, that's also what the build system does in the unpack task. Sometimes there are patches to be applied. If there's additional integration patches or whatever it is, the Yocto Project build system does it the same way. So patches are applied. Then the patch, you have this patch sources as an output, and if it's some auto tools or otherwise with the build system configured source package, you run a configuration step, and then you're building it. and then you're installing it. And typically, if you do this on a local machine, you build a software package you want to install on your local machine, then installation typically ends up putting these software build artifacts into the root file system of your local system. The build system, of course, always uses a built-up sandbox to do so. And after that, then follows a packaging step. Typically, software developers are not that concerned often with packaging. This is something that the distribution builders do, but as you're working with the Yocto project, you essentially become a distribution builder. So you have to think about how do I package these artifacts the best for my target system and for the intended use of the target system. Often a lot of artifacts are created on an embedded system. You may not need a lot of the documentation files because users won't be able to access them. Or of course, on a runtime system, you won't need any files that are necessary for software development. So splitting these out and putting these into different packaging, this is the task that we're talking about here. So far, so good? All right. This is what I just talked about, and the Yocto project always creates also a root file system from package feeds. So any software that you build with the Yocto project, any application, any libraries and everything needs to be packaged because the root file system is built from these packages. These artifacts are not directly copied into a root file system. They're always built from packages. And that may be different from other build systems you may have been using, such as Buildroot, which doesn't package. They actually copy artifacts directly into the root file system. And from then, the system image eventually is being created and bundled up together with a Linux kernel, or also a disk image with a bootloader or whatever it's necessary. All right, so I touched on this already. Packaging essentially is the process of putting these build artifacts, build output into one or more packages that's then ready for installation on your target system for a package management system. So why wouldn't you simply say, okay, why not copy the build artifacts directly? Well, you want to manage the space on your target system. You don't need all of the build artifacts. There may be documentations there, and it may not be needed. There may be libraries there, static link libraries or so that you don't need. On a runtime system, you may not need, typically don't need any headers for C headers or so for software builds and other things. Another important reason for using package management is you want to allow installation removal after the initial root file system has been created and at runtime, so for updates, essentially. And package management system, of course, also keep track of your of the packages that have been installed and what versions have been installed. So that's a great help there. You want to also detect and manage installation conflicts, things that that shouldn't be installed at the same time on the same target root file system. You also want to manage dependencies. Essentially, package managers also monitor the dependencies and see if the dependencies are fulfilled, which means if your software package relies on other software packages, if those have also been installed. And sometimes, after installation or before installation, you need to do maybe some other additional tasks, some preparation of the system, maybe some configuration that needs to be applied that only can be applied actually on the target system itself. It cannot be pre-created in that sense as an artifact and installed. So these are these pre and post installation and remover processing steps, which are typically done through script files. And as I said already, Yocto Project creates the root file system from software packages. So whether you like it or not, if you build with a Yocto Project, you always have to create a package for your software. So how does this actually work? Now, of course, you have, there's different package managers available, and dependent on your preferred Linux distribution, you certainly know about some of them. RPM, the Red Hat package management system, created by Red Hat, is used, of course, by Red Hat distributions, Fedora. It is used by SUSE, OpenSUSE, and others. Then there's the Debian packaging format. It's typically used, of course, by, oh, this is Debian, that's autocorrect here. Packaging format is used by Debian systems and Ubuntu, also with apt-get. And then there's another system that's actually supported by the Yocto Project. This is IPK packaging format used by the Open Package Management system. They differ a little bit in their functionality and what they can do and how they work. And emerge an option as packaging, not as a package management class, as I know, but I haven't checked recently if there was any additional package management classes being added to it. These three are actually commonly supported by the Yocto project pretty much since day one. So the RPM package manager is the one that the Yocto project actually uses by default. So in conf local.conf, you find this entry package underscore classes, which defines these package management classes you're using. And you can look at this if you're back to your setup here. And you look in conf, maybe I clear the screen so this goes to the top. Package classes. So while this is commented out, it's actually the default setting, so you can uncomment that. And here's a list of your package management classes there. So you can actually package with multiple package management systems at the same time. So the build system doesn't prevent you from doing this. You can actually add package RPM plus package deb plus package IPK at the same time there. And it will create all these different package feeds. However, only the first one in this list will actually be used by the Yocto project to create the root file system for your system images. But you get all of the package feeds. That's all right. You can add one or more package classes, as I said, and only the first one will be used. So while the Yocto project uses the package manager to create the root file system, it doesn't mean that the package management system and the package management databases are actually installed on your target system automatically. So if you want to use a command like RPM or apt install or something like that on your target system, you will have to add actually package management to the image features. Well, here's this my darkest dot. Guess probably better not to try to compile stuff on embedded devices. It's perfectly feasible to do so. You can add all the development packages to your target system, and as well as the compilers that are necessary for that architecture to do so. It mostly also depends on how powerful your target is and do so, but it's completely feasible, and with a Linux system, to be not a big problem. It just depends on what your target actually is, what your target hardware is. All right, so let's talk about package splitting, which is a process of putting these build artifacts into different packages. As I said, why you would want to do that? It gives you a scalability, a sort of fine-grained control over what gets actually installed as part of the package onto your root file system. And so you can control the footprint of your root file system and only put onto your embedded system what you actually really need. So how to do this? So it's done by two variables, packages and files. So packages is the list of packages that the build system creates. And a package always, of course, the package name, and then well, an additional denominator, or so I can say now. So SRC means source file package, DBG debug packages, static def, any artifacts are necessary for development, static libraries commonly. Def is any headers and things necessary. Doc, of course, documentation, locales. Package before PN, we're going to get to this, what this actually means. And then PN is kind of the standard runtime package. Now you think of this can think of this list as a list of filters. The build system and the make process or build process of your software package creates a whole bunch of artifacts, and then these artifacts are installed into different directories, such as a user lib or user bin or a user include, or into user share for docs, and and then the waiting there is ready to be packaged. And this is essentially a list of filters that are applied from the left to the right. So first, the build system looks, okay, what of these artifacts match my source package filter, and then which ones match the debug package filter, all the way to the end, where everything that is left over then will be packaged in the default runtime package. Now these are really filters, so essentially everything what is not filtered out trickles into the next filter, and so on until whatever is left over gets put into the final default runtime package. Now, this doesn't tell the build system yet, okay, so what is the filter actually? What does it need to look for to filter out? And for that, it's that files variable that's necessary. So files, and then the conditional for your package name. And then that is a list of directories as well as individual files that you want this filter to catch. And this is the default for debug packages. Now you can, of course, amend that, override it in your own recipes. That is all perfectly legal. The default settings are the ones that are, you would that follow the let's say common or standard practices of Linux systems, where to put things. Kind of follow the Linux standard base definition standards. So anything that hasn't been installed or not packaged would normally been packaged would create an error message, and that is good, because then you notice, if you have a huge software system and it's creating a lot of artifacts, and it's putting artifacts into some directory, maybe in /opt my software package or so, and it's not going to be packaged and caught by any of these default filters, you will get actually an error message at the end of the build process of your package. So then you can address this and see, well, either I want to ignore those, or I want to actually package them into put in some sort of a package. And here's a list of the default files definitions that you find and what they are. I went over this already, what they do. You can, of course, define additional packages if your software has some special requirements. You want to, that is not some artifacts that you want install separately or with your own customer package. You can do that. You just define another files $PN package name, and then, of course, you need to add that to the packages list. And so that is the, and so you can, of course, append to packages directly or so if you wanted to, but there's this nifty variable here, package_b4 PN. And that's a good place normally to put your additional custom software packages there. So if you define your own, let's say, you know, my great software dash test, and then it has some test applications or so, then you want to add this my great software dash test essentially to package before PN. Typically in your, and you do that in your recipe, you know, package underscore PN equals, and then you add the list of your packages that you want to add there. All right. There is some packaging QA going on that the build system does for it. I listed the most common ones you'll probably run into when you do your own packaging. And so it detects some of the common packaging mistakes, let's say. And it's done by the insane.bb class in the manual. And you can look this up. There's the URL on the bottom. What all these checkers are that are provided by the insane.bb class. One of them is packages list. So the same package actually is the same, has been listed multiple times in packages. So that can happen, you know, if you do another $PN or something like that accidentally or something like that. So it shows up there multiple times. So it checks for that. The next one, installed versus shipped, is an important one. May happen with any artifacts that are installed in other locations, such as the standard locations that are already addressed by the default files definitions. It's a good warning. I've seen it many times when I'm doing packaging, particularly also with customer packages or so, which I'm not necessarily familiar with. It tells me, okay, there is stuff that the make file or whatever the build system is used for that software installs into the root file system, but I have to address this in my packaging. Already stripped. So typically the Yocto project builds everything with debug symbols and so that the debug packages can be created, and strips it later than for the runtime package. However, sometimes make files strip everything already by default. And then so the debug package would not be able to be created. This happens as something you would have to address through a makefile patch or build system patch for your software package. LD flags is also something that happens every once in a while, that the ELF binary doesn't have symbols, but it has no hash, like a GNU hash for the fast symbol lookup. Static def, that means a static library, a .a is put in a non-static in a runtime package or in this default def that can happen here and there. And files invalid, the files variables invalid. Typically it has items in with a double slash, which is invalid. It's a common mistake there. If you really need to, you can disable these checkers for a package. So you can add that package to insane skip. Essentially, and say, well, look, you can add that checker to insane skip in your recipe. Say, I don't want to hear from this checker. Sometimes you need to do this, if in particular for packaging binary packages, which is something that has already built, hopefully, built outside of the Yocto project system. Typically, I wouldn't recommend that, but it can happen. So you get like some third-party libraries or things like that. Hopefully, these have been built with a Yocto project tool chain. Then you shouldn't really be running into any problems. If they haven't been, then sometimes these checkers flag things like LD flags or already stripped or things like that. Then you have to skip those checkers, since you don't have any influence over building the source code, because everything has been delivered to you as a binary. All right. So now we have a lab here. We try this out essentially. And so you have your source code. As I said, for this class, we assume that this is in Scratch SRC user space lab packaging. Sources, Fibonacci. It's a simple application that actually calculates the Fibonacci series. So we'll look at this first. So lab packaging. So in SRC, so there is the Fibonacci application there, and what it actually does is it's just a simple application. There is a simple function that calculates the Fibonacci series, and it eventually gets compiled and created as a dynamic linked library, a shared library. That's all. There's just one function in that shared library, and then there is a application that uses this library. So, and the way where, of course, you could have done everything in one source file, but we actually use this to demonstrate the package splitting. So far, so good. Everybody has this available. And I'll take that as yes. Of course, it's not as interactive when we're doing this remotely. Okay. So what you do is use your dev tool again, and you add a Fibonacci recipe or Fibonacci recipe essentially to your environment. What you do, you use dev tool add. This is what you call it, the first thing, Fibonacci, and this is where to find essentially the sources. So we'll do that. Now we'll do this where we actually have initialized our build system. Packaging SRC Fibonacci, so that should be that. Okay, so what happened now is your dev tool has added a subdirectory recipes to the workspace layer, build user space, and inside of that, it created a subdirectory for the application, which is Fibonacci. And it also created a recipe automatically for that application. So when we look at this, at the user space recipes, Fibonacci, BB. So it says so, recipe created by recipe tool or dev tool. It just populates the license as closed, makes it easier, so you don't get any license warnings or so. Eventually, this is something, of course, you would have to adjust to whatever licensing you have in your software packaging. At this point, there is no source URI because we're using this external source tree for this, and which is typically for these workspace layers. And it just puts some defaults for your for the do configure, do compile, do install tasks into this. And now the first step, of course, is you try out if this is actually working already as you want to. So you do bit bake. So it's building it. All right, so it built that. This is pretty straightforward. It's a pretty straightforward application. It has a makefile that can be used as is by the Yocto project to create the application. And it's also, you saw also the packaging steps I'm going by. It is actually the RPM packaging. So we're going to look into that. So so far so good. Did this work with everybody? All right, good. Just waiting on the build. Okay, yeah. So my apologies here. I probably pronounce Fibonacci. Oh, it does understand how source URI works now. Okay, let's look into this. Okay. So, well, okay, so that's it's a standard layer. The workspace layer, so has been added as this. It gives it a priority and everything. The trick is in that actually in this appends. It creates that BB append. So it creates this automatically for the workspace layer, and it inherits the external source class and defines here the external source, which is actually the variable where to find the sources and where to build essentially the sources. That is specific to these workspace layers that use a local source path. So anytime you use a local source path, you would inherit this external source class and you would set these variables. The workspace layer does this automatically for you. The idea there is not to convolute or to compromise your actual recipe for which you would eventually define a real source URI. Does that make sense? So it's kind of an override in that sense. So far so good? All right. Of course, now we want to put this into our image. So Fibonacci, want to put this. So we add this at this one to the end of to conf local.conf. Let's go back here. So you change the directory here, build user space. All right, add this to the end here. So now I did a copy and paste here. Now the problem is with the copy and paste. So if you do this, you can see that these quotes are kind of the stylistic quotes, but it's the wrong character for the bitbag parser to understand this. So you would have to change those. So, and then of course in this case in VI, it would actually also change the color to make sure that this is correctly quoted. All right. Now we can build this. Image base. Yes, the white space was on purpose. So since the Fibonacci application has already been built earlier step, so all we have to do is create the root file system. To add to the current image install append line, you could do that too. This window's gotten a little bit too big here for to fit on it all. All right, still working on it. Let's now shrink this a little bit more. All right. Missing or unbuildable dependency chain Fibonacci. So it cannot. So did you run bitbake Fibonacci and did that build? Okay, so so did you add that space into the image install append? Let me do another window here, another terminal. All right. Yeah, so yeah, so I missed that there is already an image install append, so you can add it to it. So if you get this probably not buildable dependency or so, it may be that you're missing that that white space here, because the append actually verbatim does actually the append, so it does not add any white spaces such as maybe the plus equals operator. So what I did, of course, here I'm actually simply overriding image install append. So actually removing well, OpenSSH and GDB server, but I don't need those. Let's see if that build is done. Okay, so let's run QEMU. All right. So I can enter the number of terms, and then it calculates this Fibonacci series here. You can shut down your QEMU again. Okay, yeah, good find, yeah, double N. All right, did everybody get that far? No feedback? All right, so good. Well, thanks for following along. Okay. Now we do something. You want to now edit the recipe Fibonacci.bb and place that Fibonacci test application into its own package to be created before the standard runtime package. And then you want to add both of them. In this case, and once you do this, your runtime package, Fibonacci, will just contain the shared object, the library, and Fibonacci test will actually then contain the application to test out your library. How to do that? Well, here it is. It's pretty straightforward. So you create your new package. You add this to package before pn. And then you define your filter for the files that actually have to go into that test package. So I'll just copy that out of here and go back. Now you can just end that to the end. And here we go. This time actually you have the right quotes here. Now we're baking this again. See if it works. Of course, it doesn't have to build anything anymore. So the shared state cache is clever enough to figure out, well, all I have to do now is I have to repackage that differently. And now all you have to do here is to do this and then bake this image again. So now once this is baked and you start again, of course, from the pure functionality point of view, nothing has changed because it was like that time before too. So you had the shared object and you had the executable application, except that they were just packaged into the same package, the same runtime, the one runtime package. But once we're done here, so we look at the root file system of our emulator, and then we'll also look a little bit behind the scenes in how this packaging actually works and how the build system does it in the recipes sandbox. So no, yeah, so Peter's right. So the Fibonacci package is not empty. It has the library, the Fibonacci.so, the shared object in there, and but the executable is in Fibonacci test. Now, you won't know that by looking at the root file system because we installed both packages. But once this is built, we'll look behind the scenes and see how this packaging and package splitting is actually done by the build system in the recipes sandbox. All right, here we go. So we're running our emulator again. All right, so yeah, every time we rebuild this, then the first start, it generates that RSA host key. And it's looking for some entropy to make this a random key. That's why it takes a while. So nothing, of course, has changed here. Same thing, but you go into user bin. That should be here. So here's the application in user bin. So that's probably maybe installed into lib. Or did it install the application into the library into? On this one, lib 60. Yes, we will have actually look which packages were actually generated and their contents too. We'll do that. Okay, so, oh, what did I do wrong? Here we go. So in user lib, you of course have lib Fibonacci, and in user bin, there is the application itself. All right, so far so good. We'll shut this down again. Now let's have a look behind the scenes here, if everybody is okay. So packaging happens in this recipes build sandbox, and in particular in two directories, package and packages split. And then the build system also creates the packaging metadata in PKG data and PKG data input. So there's some compiled packaging metadata and the source packaging metadata. And let's do this. I'll actually just here in Scratch. Actually, I can use. I don't know why that was in. Okay. So here in build user space, of course, where do you find your build artifacts in PMP work? And here, of course, organized by architecture. This is just a standard package, so it will run essentially on any ARM Cortex A657 system. So we go into this directory and go to Fibonacci, and then that's our first version there. So that's that is the build sandbox. If you have worked with the Yocto project for a while, you're probably quite familiar with it. You probably looked into temp, where you have the various run scripts as well as the debug output. What we're looking in here is package. So in package, there is everything there from that has been installed in the root file system that needs to be packaged. Now, in our case, we're really only installing stuff into user. Well, all right, here we go. And so this is how essentially our makefile has already created things and installed it, and how the build system also added the necessary debug sources. So in bin, of course, user bin, we have Fibonacci. User include, we have Fibonacci.h, the header file for the library. And user lib, we have lib Fibonacci .a, which is the static library, and the dynamic link library created from it. And then in source, debug, Fibonacci, and diversion, we have the sources essentially for it. Okay. So that is what the build system then uses for packaging, and to that it actually applies those filters that we have defined in packages, and it runs essentially the this directory, this input, through those filters. And that you can actually see in packages split. Here you have direct subdirectories for each of the default packages that has been created, as well as for Fibonacci test, which is what we have created. So if we go back, I'll go switch back and to that slide. Let me just find that. Okay, packages, and see if I can now with a smaller screen be able to overlay this a little bit so we can see both of that. So here are all the packages that are defined in this packages variable, and in our case, package before PN, of course, contains our test package. So these are all created as subdirectories under packages dash split. So for Fibonacci is, of course, $PN matches this one. Fibonacci debug matches this one. Fibonacci def this one, and so on. Now, not all of them have something in them. So Fibonacci has, of course, has user lib and lib Fibonacci in there, which is the only the library. So after we did create the test application, only the library remains in that. And then, of course, the test package now has the application. But we also have the development package. And the development package now, of course, only includes the header file for that shared library, which is necessary for development because you need to include it if you want to use the library into your own C applications. And if you go down to SRC, the source package, you see what's the sources being packaged out. We do not have any documentation, so that should, of course, be consequently should be empty, which it is. We also don't have a locale. We didn't do any localization to our application, so we would have that in locale. You would normally put any get text language files in there. But we should have static def because we do have a static library for lib Fibonacci. So does this make sense? Does it explain how this works? Any questions so far? All right, let's jump forward. That worked for everybody. So, oh, the debug package. All right, sure. So it should have. So I would normally expect that the debug package actually has the the symbols in it. So I'm not quite sure why that is not happening.
It's a hidden file. You need to use the manual.
Oh, yeah. You're right. There we go. Here we go. Yes, correct. So it's hidden files. Thank you. Or like that, yeah. Here we go. So the directory.debug is hidden. My bad. All right. So far, so good. Can we move on? We have a little bit left to do. I'm kind of almost running out of time, but if it's okay, we can run over a little bit. So package installation scripts. So that's an interesting thing too. So sometimes your software needs to have some configuration applied or whatever it is that is so specific to the target system. So you cannot do it during build time, but you have to do it during runtime. Well, actually, it's two things to it. Well, you can have some configuration that you apply during build time when the package is installed, and then there's another thing where you can apply things during runtime, during the first runtime. Yes, you can copy this debug file on the hardware to run GDB debugger. Actually, if you do add debug packages as image features to it, this will be automatically be installed as a package. So, but yes. So let's look, just go a step back here. Okay. So here, if you do an extra image features append and debug packages, then for all of the software packages that are installed in the root file system, it will also install the debug packages, which is exactly that. As a matter of fact, then, if you go and run Qemu and you look into your root file system, you will find those there. All right. Okay, so package installation scripts. So these are executed when the package is installed. These are executed whether you install the package to the build system in the root file system, in the target root, or whether you actually download a package to your target and install them there. And there is 4 of them. Pre-inst, this is a script that's run before the installation of the software happens. So if you need to massage something before the installation happens, then you can do it with that script. Post-inst, after the installation has happened. Pre-remove, before the package manager removes a package, and post-remove, after the package manager has removed the package artifacts from the root file system. And there's a skeleton, essentially. And that's what you define inside of your recipe, pkg underscore post inst, and then conditional for your package name. And this is actually typically often you use these scripts commonly for your runtime package here, but of course you can also have them for any other package if you want to. But then here you define the package name where this installation script goes into. It's always good to define the shebang here, the interpreter you want to use, and then you put your shell commands there. These are shell scripts, of course. And some package managers, RPM specifically, require you to actually specifically exit with an exit code. So that's why this is here. Yeah, you can fail, of course. Yeah, you can. If your script doesn't run correctly or so, something happens, you can put out an error message. And you can exit with a non-zero exit code. And then the installation will be marked as not being successful. This would also indicate to the package manager to roll back any changes it has done already. So this is executed as at build time when your root file system is created by the build system by doing do rootfs, which or the rootfs is created from package feeds. And it's also executed because it's part of your package, like your RPM or Debian package. When you put this package onto the target and run RPM install that package, then these scripts will be executed too there. So in both cases. Now, moving on to the next slide, there is a case where something cannot be done when creating the root file system by the build system, because the installation steps may be specific to the target. It could be that you want to create maybe your software packages some sort of a server or something like that, and it needs to create some specific identifier key or so that needs to be different for every target it runs on. And even if I install the ISO, what do you mean by the ISO? You mean like the complete system image? Well, those scripts would already be executed at that point in time, because the ISO is a system image in that sense. The post installation, the on target scripts will be running on first boot. So that's the idea of that. So you have this post ins on target, and it's executed. Well, this is a copy and paste error. I actually have to change this. It's actually executed when the system boots the first time after the installation. So I apologize for this. I'll fix the slides. It's a deferred script execution. So it does it when the system boots the first time, and it works with system D as well as with system 5 init in the same time. And the build system just takes care of it for you, so you don't have to worry about that. Yes, yeah, that's to make these open. Yes, that's kind of the idea behind it. Correct. How do you keep these from hanging the system? Well, test and again, and write your scripts right. But yes, if it takes long or so, it will take a while, and it will stop. Some system managers can also monitor that essentially, and if it never finishes, then I have a problem. But yeah. Is this mechanism resilient to power failures while it happens? Essentially, yes, because to some extent. The problem is it's not a mechanism that would exactly journal what's actually happening. It would actually, if you interrupt it in between, then the system D service file or the system 5 init script that actually runs all of these post-installation scripts in a series would not have been removed. It will be removed after everything has been completed. So when you start it again after this power failure, while this is happening, then it will go through the same steps again, which of course would mean that some of these scripts are executed once again. And if you created some host keys or something like that, well, it would create a new host key. That may or may not be a big problem. There may be some things you should only be done once or cannot be repeated. It just depends on what it is. You know, you're essentially free to put in there what you want. And race conditions between different installation scripts, that wouldn't happen unless you put something into your script that would further defer an execution, which is not recommended. And I've never tried it. If it's even possible, it would work. So you shouldn't put anything into these scripts that would send something into a background or something like that. That's actually not a good idea. So in this case, all of these installation scripts are executed sequentially. All right. So we can try this too, of course, with our Fibonacci application example from the previous lab. And we do it just simple. What we do here on our round target, we just create a file in TMP. The idea with that is just for demonstration purposes. Once we reboot the system, of course, TMP will be empty again, which is kind of the proof we use to validate that this is exactly really only executed once on first start. So we can grab these. And you can just add this to the bottom here. And of course, yeah, with your the indentation, it actually gets lost from the copy and paste here. It's actually not really necessary, but okay, just for readability. All right, and then we bit bake this again. So now once this is done, and if you have paid to your boot process of your QEMU virtual machine earlier, you may have seen this already. It says configuring packages on first boot, and it puts this there, and then eventually it will actually also show something for our lib Fibonacci. So I'll just wait for this to build. All right, well, as far as this build, are there any questions? Does this all make sense? Is it helpful? Thank you. Almost done here. Which file does the script go into? More like which package does the script into? That's a good question. It's actually the package that's denominated here. So $PN means it goes into the default package. But you could also add here $PN-def, then this script will be executed on target if you install the development package. The most common use, of course, is what I'm showing here, is having that in the default package. All right, so we're running QEMU again. Now let's pay attention to the boot process when it does our installation here. No kernel. Here, so here we go. If you saw that. So here it runs the post installed scripts here, and it puts those into rpm-post inst. If you do a different package manager, it will say, of course, dep-post inst. I'll wait for this host key again. So if that works correctly, then in TMP, we should actually see our, here we go, our file that we created. It's of course an empty file. So now you can go into etc and you see your rpm post inst there. But so the post installation process has already removed those scripts, so that they won't run anymore on the next system boot. So if you reboot it, your QEMU virtual machine, then of course, since this is only a one-time operation, TMP should be empty now when we start again. I think we're running over time, but if you guys are okay with it, we can just continue. I think there's a social then in one of the rooms with virtual beer, or you get your real beer. Okay, so it's not there anymore because it only has been created once. Yes, in this particular, well, TMP is not a read-only file system. It will probably never be, or shouldn't never be. But yes, I mean, if you try to write on a read-only file system, as mount a read-only, whatever your package post installation does, if it tries to write on a read-only file system, it will not work. But you know, TMP is a tempfs, so it's a temporary file system. It's created at runtime and recreated. But yes, I mean, if you, and that certainly can teach an entire class on doing root, read-only root file systems, and then correctly splitting things out, and have a variable file system. You would have to put those all onto different disk partitions. This is all possible. There's a lot of things you'll have to consider for that. You in particular also if you have something that writes into /etc, such as like WPA supplicants or network manager or so, when you create a network connection, it writes there. So you have to see what to do there. If you have a root file system, you can use overlay file systems to handle some of these things. So lots of stuff you have to can do this. I mean, the script will run each boot. No, this one won't run. This is it's a one-time run only. So it will only run on the first time the system boots. After that, that system service actually removes that script in etc. In this case, it's rpm post installs. So the script is not there. It wouldn't execute anymore. All right. So package groups, this is also something you might consider then, if your system uses, multiple applications, libraries, packages, whatever it is, and it makes sense to install them all at one time, which helps you with, managing your images and everything. You should consider creating these package groups. Package group is essentially a recipe with some special content, and it inherits the package group class. And as any recipe, it has a summary and a description. Summary is mandatory, description is optional. Inherits package group. Then you define a variable that's called packages. So these are essentially packages. These are actually the package groups that you're defining. This recipe can define more than one package group. So these PN databases, so PN means in this case is the name of the package group. So whatever you name this recipe, this will be the name of this package group with dash databases and appended to it. And so here we are defining 3 different package groups. And here we're defining what goes into these package groups. And you do this with an RDepends. So all the these package group definitions do is they're creating runtime dependencies, which tells the build system, if I am asked to install this $PN, and I call it maybe you call this a package group IoT device dash databases. If you put that into image install, it knows, okay, so I need to install this. It creates a runtime dependency. When I need to install this, I need to install the DB database system and SQLite 3. Okay, so going back to the one-time scripts, the one-time scripts, they are part of your recipe. They're defined inside of the recipe, so that's where they go. And no, you don't create packages for a one-time script, because the installation script is part of the installation process of your software package. So if you create a software package and you need it to do something, then on installation, or after installation has completed on target, then you put it there. If you want to have a script executed every time your system boots, so that's a runtime service. We'll talk about that just in a little bit. If you want to install scripts on your system, like that's the same thing. It is a package that you create, and then you can install those scripts wherever you want to do it. Install in user bin or install into a specific directory. They're not treated any differently as than a regular software package, except that you don't have to build scripts, and scripts are typically architecture independent, which is also something I'll get into just a little bit. So so these package groups, they create these dependencies. So for each package group you define in packages, you have to create an RDepends for that, and then you tell it what software packages you want to have installed in that. And that can be anything. I mean, you can create package groups for development packages or debug packages and things like that if you want. It's essentially a symbolic name or a name. You use it in image install as you would do with any package. Essentially, you would want to install, and the build system resolves this for you. All right. So we have a little lab for that too. So you can make your recipes package groups, and and then you can do essentially what's in this previous slide. So you can go there. We're still on the system here. So shut this down. is a package group defining 3 packages. Well, it is one package group recipe that actually defines 3 different package groups. You can, as little as 1 or as many as you want, package groups within the same recipe. So we go into go to meta user space recipes, and let's see if I need to stay consistent with what I'm doing there. Recipes, package groups, okay. So I'll do this, and then I'll simply copy all of that out of here. All right. So this should be, so of course, for some reason, any white space is always lost here. But, and one thing here is also that this one is actually incorrect. So I'll add a little bit of more spaces here to make this more readable. This is for humans, okay. BitBake doesn't care. And you can, of course, use some indentation there too to make, it's actually always a good idea to do that. All right, we're good. Should be okay. So now all you have to do is, again, you add something to your image, install, append. Now your T dash, which one do we add? Well, let's just add databases. All right, I should be able to build this, the image base. Of course, now it's analyzing dependencies again, creating a dependency cache, because of course, if we do a package groups, you're defining dependencies. So to analyze these dependencies, and we most likely haven't built any of these databases or these software packages yet. Because it's a runtime dependency, it will then first build those. All right, here, now it's doing DB and SQLite. So we'll see how long that's going to take. Maybe in the interest of time, we just let this run. We'll just continue talking a little bit. Or you can do it yourself. Just give me a thumbs up or something like that if you start building. That's not too bad. Compiling. All right. Okay. Let's talk a little bit about some packaging tips while this is building in the background. No, I did actually add package group -IoT databases. So let me go back. So here are the package groups you define. Now, this $PN actually uses the name of the package group recipe, which is package group -IoT. And then if you want to install the particular package group, you have to then add either -databases, -Python, -servers. So I just added -databases. Also, in the interest of time, you can add all three of them if you want to. Does that make sense? So I can actually, let me just use this. Yeah, just I added package group -IoT -databases to it. In the confines, yeah, conflocal.conf. I apologize for that, so probably moving too fast a little bit. It should also be still on this slide. Yeah. Well, it doesn't exactly give you the solution. So yeah, so the conf local to conf to image install append, you add your package group. And this is very convenient, you know, just by specifying one name, the name of the package group, it will install all of the software packages that are defined by this package group. Yes, yeah, you can use the, you can create a script resizing. So you would, what you would probably do is, so you create a script that you would install as part of a software package. You install somewhere in user bin or wherever you want to install it. And then you would add a post-install on target script to your recipe that actually calls that resize script. Felipe, what are you referring to in this last example? You're referring to the scripts? The link to the presentation. Let me get this real quick. Where am I? Make sure that I respond. Yes, here we go. That's where it is. All right, so far so good. Everybody building, running, doing package groups? Not. Okay, now here it's now it's installed. Now we can run our emulator again. Yes, I have defined 3 packages, but I only used one in the interest of time. 3 package group for that matter. All right. So yeah, now we installed SQLite 3, so you can run this. I think this is what it is now. This is Control D, or there we go. Okay. So you should have those. The session, you mean like my wonderful talking, or the the slides and the examples? Yes. So the slides and examples you can find from this link that's posted above here. Maybe I can pull this in here. So here you can find this from the, you can see this. You'll find that from the Yocto from this event website essentially, and then the rest. I don't know where they upload the if they upload the chat as well as the recorded meeting somewhere. That's probably going to be shared after this. All right. So far, so good. A couple of tips here. We talked about some of that already. Everything, all the build artifacts, if they're installed, you must package them too. Otherwise, you get an error message from the insane class saying you installed something that you didn't package. You also need to probably install what you want to have packaged. It needs to be installed in a root file system, which is in the sandbox essentially. So you do this either by a makefile directly. So the software develops should provide an installation target in the makefile or in a CMake script or in whatever other build environment your software package is using. Or if that is not provided by the makefile, you can actually do it by the recipe itself in the do install task. As I always say, if it's your own software packages, do it and do the install target in your makefile. The reason for that is how something is installed intrinsically belongs to how it is created. So it's always good to make it in a makefile or in a CMake script or whatever it is. You do that. And then the Yocto project can then easily actually just invoke this target, which it already does by default. We've seen this with our Fibonacci makefile that has an install target, and it just invokes it, and then it gets installed in the sandboxes root file system there. So if it's a software package over which you don't have control, you can't even, may not even maybe submit a patch or something like that to upstream, then you can do it, of course, with the do install task. You could also do it with a patch, of course, and applying that patch locally to the makefile through the recipe. That's, of course, a possibility too. Makefile installation, so it's pretty straightforward. If you have dealt with makefiles before, you know this. This is a phony target install because it doesn't create anything. And then install, you should always use the install command in this case in the system rather than copy any of that. It also allows you to create these directories and everything with the correct modes and settings. And the variables in there, $target, $destier. Destier is very important that you have that in there because the build system, the Yocto Project build system, bitbake, passes this variable into the makefile, and it points to the recipes sandbox. That is very important. If a software package doesn't have that, then it would actually attempt to install, of course, just in user bin. And that, of course, would refer to your build system's computer's root directory. And you don't want to install anything there because you're building something for a target, possibly for a different architecture. So having a destier inside of your makefile is always a good idea, never what. Even for local installations, if you want to do it on a build host, really, that would be just empty, and then it would just work the same way. And so this is how the default do install task actually looks. So you run make install destier and $D, which is points to the recipe sandbox, and it passes espindir and others, mandir and so forth into it too. So using these variables inside of your makefile makes a lot of sense and makes your life much easier. All right. Recipe installation, of course, you can do it in the recipe too. Sometimes it's sometimes it is necessary. You either overwrite the do install task or you do a do install append, of course. Always again use the install command, use $dir for the sandbox, and then anything like bindir or sbindir, libdir, as so forth, as a respective subdirectory. And these are the common ones that are actually defined in metaconf bitbake.conf to use. So just a reference here, you will find them in there. Okay. Package debugging, we looked a little bit into this already. So what do you do if something goes wrong? There's always a log files in $workdir /temp. Check your installation artifacts if they have been correctly installed in $workdir /image. So if you go there, we did this for our Fibonacci. So keyword cortex Fibonacci. All right. So here in image. So inside of image, let's do a tree actually. You see everything that is installed. This is the install that the make file actually does, and $d actually points to exactly this directory. And so here you see if all of the artifacts have actually been correctly installed, and then they get actually used for packaging later. Okay. Check the part of packaging artifacts that what even get packaged. So what happens then is the build system copies everything out of the image directory into the package directory of which it knows that needs to be packaged. And this is also how it decides or finds if something has been installed in image versus it has been packaged or not packaged. So that's what this class and what this installed versus shipped checker actually does. We looked also in packages-split. So this is your package splitting. So there you can check if everything ended up in the correct package. That's where it's staged here. And then finally, the created packages are actually created in deploy package manager. So we only do RPMs here in this case. So here you, and that's of course, that is actually by architecture, because you can actually, typically your runtime packages are packaged by architecture, but some packages could be architecture independent. And these are the RPM packages. So these packages can be copied as they are to the target and be extracted there with RPM. And this is also the build system puts those into the package feeds from which then the root file system is installed. You probably know where you can find your package feeds. Deploy RPM. So here are your package feeds and Cortex. There you would also find, of course, our Fibonacci packages, of course, and then the Fibonacci package itself. Good. Check also package data recipe, also for the list of packages that have been created in what order inside of the recipe sandbox. All right, package architecture, that's a point. Often you don't really have to worry about it too much, but the build system actually does this pretty much automatically. Like most of the software packages, of course, they like C compiled things like C, C++, any of that. These are typically generic, based on the generic CPU architecture, such as Core 2, not of course, 32 or Cortex A57 or something like that. And it's typically appropriate for most of the software packs. You don't have to change it. Some software packs can be very machine specific, which means in this case, machine does not just mean CPU architecture, but means they're specific to the hardware that CPU is actually working on. And that's typically good for any package to require particular hardware features of a machine. It's applicable to kernel, drivers, and bootloaders. These are machine specific. Okay, well, let me just answer some more questions here. Any architecture and packages apply to architectures with shell scripts or some managed runtime or so, some bytecode, which could then, they can run on any system, but of course the runtime system has to be installed, such as Java or Python or Lua or so, but the Python code itself is machine independent. This is all controlled by a package arch variable. So tune is the default and it's used. You don't have to override it for most cases, unless you have Python scripts or so, then you just override it for Python. But even like DevTools, you can figure that out automatically. It's not just a category in that sense. It also, it also defines what compiler and linker flags and other build options are passed to the tool chain. All right. I'll scroll back a couple of questions here, Mr. What is the difference between image and package directory? Yes. So the image directory in the recipe sandbox contains all of the artifacts that have been installed used via the install target, either do the do install task, either do install directly, copying, installing this, or through a install target that calls from the package build system, such as make. When Bitbake then goes through the packaging, it actually analyzes what's in that packages variable and in the files variable. And then it actually moves copies what's in image into the packages subdirectory. And this is how it actually finds out whether, whether there's anything that has been installed, but it's not contained in any or not addressed by any of these package filters. Does that make sense? Yes, so we have the same thing, and it should actually always be the same because it means that we packaged everything that we actually installed. All right. Let's move on. So last but not least, talk a little about system services. Of course, often you have, you do a device or so, eventually you have to start some software on system startup every time. It provides a user interface or whatever it does, or some other service or whatever it is. And so you need to add these startup scripts or service files, startup scripts for System5 init, or service files for systemd to the system. And your recipe has to inherit the respective class to package and create everything correctly. So for System5 init, you inherit the update-rc.d class to deal with System5 init startup, and the specific variables for that are init script underscore packages. That's a list of packages that contain init scripts. It's an optional variables defined by default to be just $pn, the runtime package, which is typically adequate. But if there's something that needs to be started in some other package, or so you have your own packages or things like that, so you would actually add your own package to this. And then the name of the init script, which you have to give it the name, and you also have to provide the init script essentially as a file. And that file can already be part of your source tree, or you can actually provide it separately through by putting it with a recipe. And then your parameters for starting and stopping the script. These are passed to update-rc.d. Typically, these are star 9935. That's a different run level, the priority and the different run levels. for starting and stopping. Systemd is different, but the idea is the same. So you have to inherit the systemd class to do so. Systemd packages is the systemd analog to init script packages. So you list all the packages that do contain systemd service files and need them. And then the systemd service $p, and that's the name of the service file that goes into that package. And so we have a lab for that too. In Scratch SSC user space lab system service. So we have a Fibonacci server here. Essentially, it builds a TCP server, it listens on port 9999 for the number of terms and responds then with a list of Fibonacci terms. And so you can do that in your environment again. So let me just go back to build user space. So the first step is DevTool add Fibonacci service Scratch SRC user space lab system service. All right, here we go. So it does that. So if you go into meta recipes, so we have our server here. So we have our, DevTool already created our script and everything for it. Of course, it doesn't know anything about that. This recipe actually is a recipe for a system service. So we have to add that. And we simply do that. So you can copy this out of it. And of course, so here we have to actually change these quotes again. So here init script name, of course, Fibonacci server.init, and for systemd it's Fibonacci-srv.service. So I created those already, and they're there with the sources, so you don't have to worry about those. But I'll just show it. So lab system service. So here we have the Fibonacci v.init, that's the simple init script here to do so. And then we have something also for our systemd service file. Both init system. Well, no, I'll get to that. It only uses one of them, but the recipe is prepared to work for both. But which init system is used by your target system is part of the distribution configuration. I'll talk about this in the next slide. All right. So this should be all good now. All right, and just go back here. I'm just baking this. Should just be doing this. All right, we're all done. Now, of course, the next step would be we're building this, and we add. So we talk to our server using socat. So we want to have socat also installed on our system. Conf local.conf. So I'll just simply remove those now. You can leave them too if you want to. So cat, so big core image. Nope. Face. Let's build that. So it's going to take a little bit probably to build our root file system, and then we start it up and see if that works. While this is going on, is there any questions? So you have, somebody says there's no audio anymore. Well, Himanshu lost audio. If you can all hear me still, then it may be just a local issue. The session is recorded, yes. Although I never listen to my own sessions. I always never like how I sound on recording. I don't know. All right, almost there. Well, while this is doing this, in the interest of time, and go back to that, I'll just talk about it. We don't have a so we don't have a lab for this, but I'm running a system service as a user. So by default, this would be the system service would run as root. Now, it's not always a good idea to run everything as root, in particular if your system service launches a UI application or something like that, which is a common thing to do for an embedded device that has a touchscreen or something like that. So, any UI application also has thousands and thousands of lines of code that are not necessarily always tested everywhere and vetted for any security issues or so. So it makes a very good idea to not run a system service in this case as root. And you can do this too. Essentially, you have the user add class, and you can add users and groups in the recipe that will be created then for your recipe. So you do this with inherit user add, and then your user add packages. So typically do this with a runtime package again, so it's common. And then you specify the parameters that you add to the user add command. In this case, we're saying, okay, create a home directory, and the home directory is home username. This user is allowed to log in. We give it a login shell -h. We also tell it create a user group with the same name as the username, and also add this user to additional groups. And then finally, of course, here's the username that you put there. And with -g groups, I mean, sometimes, you have a UI application, maybe it needs to access some sort of a hardware device, like a serial input-output, an RS-232 to 485 device or something like that. So you will add maybe -g dial out to that, so that this user can actually use the device. And so that's pretty much it. Now, that of course means, well, you have added the user, but it doesn't necessarily mean, or does not mean that your application is automatically run as this user. You have to tell your init script or your systemd service file to run as a user. And in init script, we use the stop daemon command to start actually our background application. We specify the user and optionally the user group. You also create this process ID file that allows then to find the process again, to stop it. And this is the command that you execute, and what other options you have to pass to your service here. And similar for stopping it. Systemd service files are a little bit simpler in that sense. We just specify the user group, and if you want your application to have a working directory, that could be then the username's the home directory. So far, so good. Let's see if this is done. So this is done now. Running our QEMU again. And I'll go quickly back to that slide where we had that. All right. Okay, here we see it started our Fibonacci server there. So we log in. Let's try this. So cat TCP localhost. It's a classic server. It doesn't tell you anything. Let's see. All right, here we go. You type in the number of Fibonacci terms and responds with your with the series of those 20 terms. All right. And since we went through these slides already, one more slide is about the system manager. That was already a question in the chat. How does this work with having sys5 init script as well as systemd? Now, of course, the system only uses either one of them, and that depends on what system manager has been chosen. Typically, that's done through, you typically do this in the distribution policy, so in your distro, whatever conf file. And the Yocto project still uses system5 init as its default. When I do distribution policies, I always change it right away to systemd. I prefer systemd now over system5 init. And this is essentially how you do it. First, you add to your distro features the systemd as a startup manager, and then you tell the build system to use systemd as the init manager with as variable virtual runtime init manager systemd. And that would still install system5 init artifacts and things like that. And if you want to exclusively use it, systemd, you would remove it entirely from your root file system by using this distro features backfill considered sys5 init, because that's kind of a dependency. So you're telling it, don't worry about it. I have something that does the system management, and virtual runtime init scripts remove all of those init scripts, make them empty. And this is then a system that's completely switched to systemd.
Rudolf,
yes,
you should really update this slide to use the init manager variable instead.
Oh yes, yeah. Thank you. That's true. Yeah, I should do that. That's the old syntax. Thanks. I'll do that. Maybe I'll do it and then I'll update it on the server too. Okay, so that's it. Well, thank you for your time. Thanks for being here and hanging out that long. We ran quite a little bit over time. I hope it was useful.